So maybe let me first apologize that last time when there was this reduced quantum group, I gave a wrong proof for the fact that the Haas state is faithful, but thanks to Ishan, this got noticed, and I will just tell you the reference. So this was 2.4 or 2.5. And we had that if we have a compact quantum group, there always exists a Haas state H such that we have this condition. And this is not always faithful. But on the reduced version it is. And here this is obtained by via GNS construction. And if you want to see the proof that this Haas state is faithful on this reduced version, then this is the book by Neshveyev under construction, and there it is, corollary 1.7.4. And as Ishan said, you need some KMS condition to prove this fact. Okay, so these details can be found there. But today we want to do some representation theory of quantum groups. So I will be a bit brief at some points because I want to write down several facts or several statements, but I won't prove all of them. This is just to inform you that there is some representation theory, and I will also again give some references, so if you want to see some details, then take a look. Okay, so maybe I should again have this line. Writing below the line is too complicated for the last row of seats. Okay, so representation theory. And Tanaka-Krein. For quantum groups. So what should it be, a representation of a quantum group? So again, let's first take a look at the classical case. So let G be a compact group. And let U be a finite dimensional representation. So what does it mean that it is a finite dimensional representation? Well, this should also be continuous. So first we know that this Hilbert space has finite dimension, and we can identify it with some matrices, and U is continuous. Thus, this matrix U can be seen. So thus it is a function from G to this space, a continuous function, and we can always write such an algebra as C of G tensor MM of H of C, of course, as a matrix. Okay, so sorry? No. Again, something's wrong? No. Okay. So this means we can write it as some sum of, say, U alpha beta tensor E alpha beta, some alpha beta. So maybe now I Yeah, that's okay. Okay, so we can always write such a representation U like this, and it has some coefficients which are in our algebra. And of course, this is an easy step to go to the quantum groups now, because then we just replace this by an algebra, and then we have more or less what we have here, right? So this is okay. So a representation of a quantum group then should be some element U in the matrices over our algebra. But let us now capture the fact that U is a group homomorphism, which just amounts to saying that UG of H is U alpha beta of GH tensor E alpha beta, which we of course can just write as the co-multiplication applied to alpha beta GH tensor E alpha beta. So this is this formula, and now this is a group homomorphism, so this is the same as UG times UH, which is, if we write it down, alpha beta, and then we have some gamma, U alpha beta G, U gamma beta, oh, this is a gamma, alpha gamma of H, tensor E alpha beta. Okay, I just wrote down what this expression means. Now, comparison of the coefficient, we just see that this should be the same as the sum over the gamma of this expression. And again, just by the identification of this with the, so if we have CG cross G, this is the same as CG tensor CG, we see that here we just have U alpha gamma tensor U gamma beta like we had before. Okay, and we get our rule for this matrix U. What should it satisfy? This is now this definition. So we take a compact quantum group, and a finite dimensional representation is a matrix U in, maybe let's call the coefficients U alpha beta, in MM over A, such that delta of U alpha beta is the sum over U alpha gamma tensor U gamma beta. Okay, this is really just deduced or being inspired from the classical case. So we have this formula, and of course, I mean, we're not surprised by this formula. This is really, again, just matrix multiplication. And we say that this representation is non-degenerate if it has an inverse. So maybe let me call this U. Then U is non-degenerate. If it's unitary, then it's a unitary representation. Okay, so this is a definition of the finite dimensional representations. We could also give a definition for infinite dimensional representations, but I will omit this in this lecture. So there is a definition, but it involves a slightly more complicated structure, and for most of the things we do, we won't need it. And if you're really interested in the hard details, then just take a look at the references. So this is this is the survey by Maas and Vandale, definition 3.5, and for infinite dimensional, This is definition 5.1, if you're interested. So the nice thing of the representation theory is that it behaves quite nice with or that it allows us to give some characterization of when a C-star algebra and a delta is a quantum group. So there's a lot of things hidden in this representation theory, and the first theorem is the following. So if we just take a C-star algebra with a unital star homomorphism delta, and now if it is generated if A is generated as a normed algebra, by the matrix elements of its non-degenerate finite dimensional representations, then it is a compact quantum group. Okay, so this definition over here, I gave it for a compact quantum group, but of course I can also just write it down for a C-star algebra together with such a star homomorphism. I don't use any quantum group structure here, and if this algebra A is generated by all these elements U, alpha, beta, then it is a quantum group. Okay, so this is a statement here, and we can refine this a little bit.
You assume delta is co-associative?
No, I guess at this point it's just a star homomorphism. Oh, let me see.
It's okay, just with star homomorphism.
Yeah.
Saying that this is a representation means that you have the equation with delta, and saying that they generate means that you have the equation with delta.
Yeah. So in fact, if I only have this is already enough, because from this it will follow that it is co-associative. Yeah. Okay, so this is my first statement. I will refine it now a little bit. Now, if A is generated as a C-star algebra by elements Uij such that delta Uij is Uik tensor Ukj, and U as well as its transpose are invertible, then again it is a compact quantum group. Okay, so this is a bit refined, and maybe before I prove it, I can already state the corollary. Namely, the corollary is that every compact matrix quantum group is a compact quantum group. So I had this as a remark before, but this is the proof now here, right? So this is exactly the definition of a compact matrix quantum group, and now we know that it is a compact quantum group. Okay, so let me maybe just say a little bit about the proof of this.
So there exist examples where the matrix elements of unitary representations do not generate?
I don't know of such an example, to be honest. So an example where the
non-degenerate ones generate, but when the unitary ones do not.
No, but you can, if non-degenerate, then you can uniterize it, in the compact case.
Okay.
It is, every non-degenerate one is equivalent to something that is unitary.
Yeah, so this will do in a second. Yeah. Okay, so a little bit about the proof. So first, from this equations over there, it follows that this is co-associative. This is really just doing it by hand, like when we proved it for the compact matrix quantum groups, that this is co-associative. If you just write down the relations for the co-associativity, then you have something like this. Then you apply delta either in the first or on the second leg, and then you will get again such an expression. So you have these sums. This is really straightforward. Like was it chapter 1 or 2? I forgot. Like before. And maybe for maybe I should say. Of course, you do this. You take a non-degenerate finite dimensional representation. You check it for all these coefficients, and since A is generated by this, then you have it for the whole algebra A, right? So you have to prove that delta is co-associative on the full algebra, but you check it first on these coefficients, and then you have it on the whole algebra. Okay. So as for the density condition, now let maybe W alpha beta be the inverse of some non-degenerate finite dimensional representation U alpha beta, and then we have that delta U alpha beta times 1 tensor W gamma beta. Maybe I should also take a gamma here. What is this? Well, this can be then seen as maybe gamma epsilon of U alpha epsilon tensor U epsilon gamma W gamma beta. And now I see that I have here a sum over these gammas, and this is exactly the matrix multiplication of U with W. This is one is the inverse of the other, so I have U alpha epsilon delta epsilon beta, since one is the inverse of the other, and this means that I exactly get U alpha beta tensor 1. Maybe. Okay, so I get this. Reading it from right to left, I see that such an element is always in this span of delta A 1 tensor A. Now I can prove that it is also multiplicative, so when I have two elements in there, then also the product is in there. And by this I can conclude, so check that if A tensor 1 and B tensor 1 is in this one, then also the product and hence I conclude that A tensor 1 is in this closure. I do it for 1 tensor A as well, and then I see that this is the whole, right? So the density condition for compact quantum groups is fulfilled. Okay, so this was one of the conditions, that this space, or to be more precise, the span of these elements and the closure.
Get one tensor A.
One tensor A. I think with similar computations like this.
No, but you need the fact that delta of A times one tensor A is tensor A tensor A, right?
No, this is what I want to prove. So I want to prove that A delta is a compact quantum group. So I want to prove that this is the same as this.
Yeah, so you have just proved that A tensor 1 is there.
Yes.
What about one tensor A? It's because you are multiplying it on the other leg.
Yeah, but I think it's really some same ideas like this.
You have to multiply the inverse on the first tensor, right?
Yeah.
So there you are using elements from not from one tensor A but A tensor 1.
Okay.
Use the transpose inverse of the.
To be honest, I didn't check it for the other thing, but I guess it should be more or less straightforward. I don't think that you need some.
No, you want, because you are allowed to multiply only by one tensor A on the right.
Yeah.
But to get U alpha beta at the second tensor, you need to multiply the inverse on the first tensor on the thing. You are multiplying one tensor W gamma beta, right?
Yes.
And you have to multiply W gamma beta tensor 1 to get the equation. That is A tensor 1.
Yes. Okay, I didn't check it. I think it should be more or less straightforward. So maybe you can also do something like.
A model like that, and then we stabilize this side also. But the A action doesn't get the A side. Which is a model. Delta A on tensor A.
Yeah, that's
By the right level action.
Yeah. So I can try to check it again, but I think it's really that there's no secret hidden there. It's again just algebra. Okay, so we see that in the end, this is a compact quantum group, and maybe let me also just check B, and that is U star, which is just U transposed star. This is invertible. What I'm writing here. This is invertible since the transpose is. So I'm assuming that the transpose is invertible, and from this I can conclude that, okay, so maybe this looks a bit strange. What do I mean here? Yeah, I guess I probably need U bar here, and
This is by assumption, right?
yeah, I wanted to use A. Okay, so now I'm a bit.
I mean, if A is invertible, then A star is also invertible, right?
Yeah.
So that's what you want to use.
Yeah, exactly. That's what I want to use. So this is invertible, and yes,
You need to have some relation with these.
and So this is the same as this one. So this means that these are non-degenerate representations, and then we may use A. Okay, let me see if this makes sense. So what I wanted to say is that okay, so if U and U transpose are invertible, then this U bar is a non-degenerate representation, and it generates my A, so I'm done.
Yeah.
Okay, so this is so if I only have that this U and U transpose are invertible, then already this is a compact quantum group by just using A, and yeah, as I said before, this proves that compact matrix quantum groups are all compact quantum groups. Okay. Okay, sorry for the confusion at this point. Okay, so let me now come to the point that we.
Do you consider representations which are not degenerate, which are not non-degenerate?
So I have representations.
Do you consider representations which are not non-degenerate?
Well, in the end, I don't consider them, but.
Non-degenerate means the invertibility of the matrix U, right? But that is
Yes,
a natural demand, right? Even in the compact quantum case.
That's true.
Compact group case.
yeah, that's true. Yeah,
So, okay.
yeah. So that's true. It's very natural, but yeah. But still at this point, I need to check it that it is non-degenerate, right? This U bar. Okay.
Shift on the position, and then we in this compact.
Okay. So next we want to show that we can always decompose representations into irreducible ones, and this is a nice theorem. I think I screwed my numbering a bit, but I think it's 5. That's true, yeah. But let me see. Yeah, I hope I will do now. So here's the representation theory. So the first fact is that every non-degenerate finite dimensional representation is equivalent to a unitary representation. So this is what, so this answers your question. So what do I mean by equivalent? This means there is an invertible intertwiner, which means there is an element in B of, let's say, HU to HV invertible, maybe let's call it T, such that TU equals VT. Okay, so this is a definition for equivalence here. So when we say that instead of considering non-degenerate finite dimensional representations, we only need the unitary ones. And second, every unitary representation decomposes into a direct sum of irreducible finite dimensional representations. Okay, what is irreducible? So this means that so if there's such an intertwiner between U and itself, then it must be a multiple of the identity. So the morphisms, so these intertwiner morphisms between U and itself must be multiples of the identity. And the third thing is there's a right regular representation containing all irreducible ones. Okay, so this is about representation theory. Here, I guess I do not really want to prove all the details. I just want to sketch a little bit the ideas. So for A, if V is a non-degenerate finite dimensional representation, then we put Y as the identity tensor, the Haas state of V star V. So this V is a matrix over the algebra, and we apply V star V. So we are still in the matrix over the algebra, and if we apply the Haas state to the elements from the algebra, we're in the matrix over the complex numbers. And so I mean, this is V does not need to be unitary, so this can be different from 1, but still one sees that Y is positive. And one can also check that it is greater or equal an epsilon times the identity, and then we define W as the square root of Y times V. So we dilate V a little bit with this operator here. And first, this is of course then an invertible matrix, so this fits into our definition of equivalence, and W and V are equivalent, and W is a unitary. Okay, so I don't check these details, but just to let you know that in order to jump from this non-degenerate representation to the unitary one, I use the Haas state here. Okay, so Haas state is useful.
You need to check that Y is actually an invertible element, right?
Yes. I need to check it. Yeah.
No, but if the Haas state is not faithful, that could be 0, right?
It will be faithful on this. This is only on the dense Hopf algebra where it is always faithful.
That's true, but at this moment we don't know it. So.
You don't think, because so V is not degenerate.
Yeah, it's invertible. Yeah.
And this is positive, so you must suppose that V star V is more than epsilon times 1.
Mm-hmm.
And then if V star V is more than epsilon plus 1. So epsilon is positive, then this is. That's good.
The same holds true for when applying this. Yeah, that's true. Yeah.
It's just using positive.
Yeah, since this is invertible, we know that this is somehow greater or equal than some element, and then applying the Haas state, it's still valid. Okay.
Same thing, any positive thing is faithful.
B star B is an invertible element. It's invertible. So B star B is the spectrum should be away from 0. And so B star B is
B star B is greater than epsilon, I agree.
hence if you apply one tensor height,
H upon is 1.
H upon is 1.
It's positive, right?
Yeah, so then since H is positive, it transports this staying away from the 0 to the Y. Okay, so this is some modification of this V using the Haas state. This is why I wanted to say a little bit about this of the proof. And as for B, you mainly just take some minimal projections, and you project down your representation with it, and then you're done. So So this is not so complicated. You have some minimal projections, and this gives you some sub-representations, and they are irreducible, and then you have this decomposition. And as for C, yeah, maybe I will also skip C. So just to let you know that there is some right regular representation. So if you're interested in what this is, you should take a look at the survey of Mars van Dale. And this contains all irreducible representations. So there, maybe this is. I think it's section 6. But you can convince yourself that such a representation exists. And from this representation theory, we now find a dense subalgebra in our A, which has a lot of properties from A, and this is a Hopf algebra, and this is my next theorem. So let this be a compact quantum group, and let A0 be the subspace of A spanned by the matrix elements of all finite dimensional unitary representations. Then we have that A0 is a dense star algebra. Furthermore, if we restrict delta to A0, this maps in A0 tensor A0. So here, this is just an algebra, so here this denotes the algebraic tensor product, or if you prefer, you can also use this symbol if you want. I don't know. So this is the algebraic tensor product. And together with this restriction, we have a Hopf algebra structure. And I will tell you in a second what it is. And my last claim is that the Haas state is faithful on this. The Haas state is faithful. Okay. So this is a nice theorem because this allows us to jump between different worlds of quantum groups. I mean, in the beginning, when I said what is a quantum group, I told you a little bit about different approaches to quantum groups. So different people understand different things under quantum groups. If you have a C-star algebraic background, you might want to use this definition of Voronowicz of these C-star algebraic compact quantum groups. But others that have a purely algebraic background, they want to use maybe just Hopf algebras. Okay? And these two worlds are linked with this theorem, because if you start with such a C-star algebraic quantum group, you can pass to the purely algebraic one just by finding this A0 sitting inside of H and restricting the delta, and also the Haar state is faithful on this one. And you can also jump back. So when you start with such a Hopf star algebra, you can complete it and then you get some C-star algebra above it. Okay, so this is maybe nice for those people that want to jump back and forth between these two worlds. And maybe if you want to read more about the properties that the C-star algebraic one has and the algebraic one, then you might want to take a look at Thomas Timmermann's book. So see see section 5.4 of Timmermann's book for details. Okay, but let us prove at least some parts of it, or get an idea of the proof. Okay, so why is this a dense star algebra? Well, if you take the coefficients of one representation and the coefficients of another one, then their product they are the coefficients of the tensor product of the representations. So it's an algebra. If u ij and u beta kl are the coefficients of representations, their product are the coefficients of the tensor product of the two representations. Which I might not have been defined yet, right? Okay, that's not so clever. Sorry. Okay, so the tensor product, if u is say this one, and v is this one, so these are two representations, then the tensor product is given by Eij tensor EKL tensor, and then the product of the coefficients. Okay, so this is maybe in MNU of A, this is in MNV of A, and this is in MNU of A. Okay. So whenever we have two representations, we can form the tensor product, and their coefficients, and the tensor product is again a representation, and the coefficient is just a product. So we have that this A0 is really an algebra. And yeah. And as for the adjoint, it works in a similar way. So if you have a representation, then the adjoint is a representation again, and the coefficients are the adjoints of the coefficients of the starting representation. And for the density condition, you have to work a bit more. So I will skip this. Okay, but it's also not so complicated. And also,
It is the U bar which will be a representation, right? It won't be there. If it's a representation, U bar will be the representation.
that's true, yeah.
That's all. Yeah, no, but why U bar is not because U star is floating.
We see.
Yeah, U bar is inevitable because U is
Yeah. Yeah, I don't think that there's a problem there, yeah. Yeah, okay. Okay, so B is also a bit technical. But maybe let me tell you a little bit about this Hopf algebra structure, because I didn't tell you so much about the Hopf algebra structure. So what do I mean by this? When we began with the definition for a quantum group, we said, okay, when we want to have a non-commutative version of it, we take the algebra of functions and we turn it non-commutative. So this is some non-commutative C-star algebra. And then, since our group G comes with a group law, this group law dualizes to this co-multiplication. Okay, so this was our initial approach to quantum groups, how we came up with having a C-star algebra and this co-multiplication with some properties. But of course, you could say, well, a group is more than just having a group law, because you also have an inverse and you also have a neutral element. Okay, so when dualizing these approaches, inverse and a neutral element, you come up with the following maps. So we define, in our case, we define linear maps epsilon as just mapping uij to delta ij, and S of alpha 0 to this element. And these maps, they dualize the idea of a neutral element and an inverse. Okay, so what is a neutral element? A neutral element is somehow you have one element and this maps into the group, and if you go to the function algebras over it, you get a map from the functions over the group to the functions over a single element. The functions over a single element, that's just C. Okay, so if you read this as functions of the group to C, this is really the dual map of mapping one element into G. Okay, so this is somehow the dual object of a neutral element, and this is the dual object of an inverse. An inverse is a map from G to G. So on the algebraic level, it's a map from the functions over G to the functions over G. So something like this, and it wouldn't be the dual of a neutral element and an inverse if it would not satisfy a few conditions. Namely, for instance, that is, we have the following relations: epsilon tensor identity delta A is the same as this one is the same as A. Okay, so what do we have here? We have here something like this is the group law. Here we have something like we take an element and we multiply it with a neutral element. Well, what should come out? Just the element itself, right? So if you write down this equation just for the functions over some group, you see that this is really just the explanation of saying we multiply with the neutral element and the element comes out. And we also have, so I will check this in a second, and we also have, if we take the multiplication of S tensor identity tensor composed with delta. This should be the same as doing it the other way around. And this is epsilon, where M of A tensor B is AB, it's the multiplication. So what is here? Well, in some sense we take elements and we multiply one with the inverse of it, and then it should be the neutral element in the end. Okay, if you again write down this line for algebra of functions, you will see that this is really it characterizes having an inverse element. Okay, so I didn't do this in the first chapter, so it's in the script, but I left it out because of the time. But if you just write it down what this means for a classical group, then this is really just having an inverse. Okay. And why is this true here? Well, okay, that's just straightforward. Identity tensor epsilon of delta uij alpha. This is the same as k. Now the first element uik alpha epsilon ukj alpha. This is delta kj. So this means the only thing that survives is uij alpha. And if we do this for all extensions, then we get here the identity function. Okay, and the same is for the multiplication.
By UAG alpha, you mean you choose one representative for every unity representation.
Yes, so I choose
I mean, this thing is true for any unit representation. This exactly this thing.
The definition of epsilon and A.
Yeah, there's no point. Yeah, but you can do it otherwise also. But yeah, for this definition, you have to do it.
No, but then you have to show that these different inequivalent representations span A naught this linear space, right? And they're linearly independent.
I guess at this point I don't need that they are linear independent.
But span is needed.
Span is needed, yeah. Because here I just take a finite dimensional unitary representation, check that this is true, and since they span A, I'm done, right?
Is it?
No, you need the basis to be well defined. You need the fact that they form a linear basis, right?
Because because otherwise you mean there might be some contradictions.
No.
You show that this is because the scalar product between both. This is some of the lemma you explained. This is because the pairwise non-equivalent. And if you take some scalar product between two different, you take the R state, then this is zero because it's not. If it's not zero, it will give you some interpointer between the two representations. They are non-equivalent.
Okay, but it's true. Maybe I left out the fact that they are linear bases here, right? Yeah. Okay. Mm-hmm. Okay. Yeah. I tried to simplify some of these statements and proofs a bit for this lecture in order to cover the whole representation theory in one lecture, but it's true that I maybe left out this detail. That's true. Yeah. Okay, but yeah. So this way we have this Hopf algebra structure on this dense subalgebra, which allows to use the machinery of the purely algebraic quantum groups. So the Hopf algebras here. But well, one should be aware that it's a bit subtle, the question whether this Hopf algebra structure extends to the C-star algebraic structure as well, because there sometimes this antipode, for instance, this might be unbounded. So this is why this algebraic structure of this Hopf algebra, this is really only on the dense subalgebra and not on the full C-star algebra. But nevertheless, there's a lot of information contained in this A0, and a lot of nice things can be done on this algebraic level and then lifted to the C-star algebraic one. Okay, so this is maybe the remark I wanted to make at this point. Okay, maybe the the reference for the details. It's again the survey of Mars Van Dale, and there's also the proof for the faithfulness of the Haas state. There you don't need some KMS. Okay, so maybe first good to know that co-unit and antipode of Hopf algebra are uniquely determined. So this is in Neshvayev's script. And maybe second, if you start with the Hopf-Star algebra such that A0 is generated by an algebra with matrix coefficients, then there's a compact quantum group such that this A0 sits inside. So this is what I said before, that you can also go the other way around. You start with this algebraic object and then you get the compact quantum group object. So starting with the Hopf algebra, we may associate a compact quantum group A delta such that A0 is in A in the sense of theorem 3.7. Yeah, and in general the antipode on the C-star algebra needs not to be bounded. Or in other words, you cannot extend the antipode to the C-star algebraic level. Then I was last time I was mentioning something of Katz type, so I said that this Haas state, so last time we developed the theory of the Haas state, and I said that this is might be a trace or not, and if it is a trace then we say it is of Katz type, and we also have a characterization of this Katz type in terms of the antipode. So let A delta be a compact quantum group, and let A0 delta 0 be the Hopf algebra inside by theorem 3.7. On S be the antipode on A0. And then the following are equivalent. First, the Haas state is a trace. So this is A delta is of Katz type in the sense of the definition in section 2. Second, S square is the identity. Third, S is star preserving. So this can be read in Neshvayev's book. So this means that we have this characterization of being of Katz type, namely if the antipode is a square of the identity, if the square of the antipode is the identity, and yeah, it's as I said last time, some people would consider Katz type quantum groups as being closer to classical situations, because when you have this the maximal group C-star algebra, for instance, then they're always of Katz type. And some people are more interested in non-Katz type quantum groups, like the Woronowicz people in Poland. Others might find it nicer to work with Katz type C-star algebras, Katz type quantum groups. So yeah, just to mention that this characterization exists, and maybe also tell you one example of Katz type and non-Katz type quantum groups.
U is a unitary, then U bar becomes unitary, so this problem disappears.
Yeah. So first, we had these quantum groups Sn plus, On plus, Un plus, and they are of Katz type. With using these two maps. So when you take a look at the defining relations of the C-star algebras that are associated, then you will see that these elements, they also fulfill the relations. So you have, by universal property, you have these maps, and then you can check that these epsilon and s fulfill exactly the defining equations of a Hopf algebra from one of these last propositions. And since we know they are unique, we know that this is exactly the co-unit and antipode that we have on these quantum groups. So since we see that S square is the identity, this is a Katz type, since this is a homomorphism. And then we also had this SUQ2 of Woronowicz, and we had these Q-deformed versions of On and Un, and they are not Katz. And yeah, so maybe I won't write down the proof for this, but I think this was one of the motivations for Woronowicz to define his SUQ2, because he wanted to go beyond the Katz algebras that existed at the time, and he wanted to have one example where this is broken. Yeah. And one can also see that these matrices Q, if they are not the identity matrix, then also these deformations are not Katz type. Okay, so and I guess the point there is okay. Maybe I just what are these structure maps? So check that again. This epsilon as before is the co-unit, but for S we have to define it like this. Something like yeah, okay, maybe this is defined as some matrix BIL UMLAMJ. Oh, maybe it's nicer like this. Q star Q inverse, and from this one the ILth coefficient, and then the MJth coefficient of this matrix. Okay, so if you define the map S like this, then it's just a linear map, and it has these properties, and you see that it is not star preserving, so it's not Katz type. So if you define the epsilon and S like this, then again you just check that the properties of the Hopf algebra of these relations are fulfilled. So these are the right structure maps, but it's not star preserving, or the square of it is not the identity. Okay. Maybe one more remark. We may also define the dual of a quantum group. So we may define the dual of a quantum group. So recall that I said one of the motivations for quantum groups was this Pontryagin duality. So if you have an abelian group, then the dual of this group is an abelian group again, and if you take the double dual, then you get back the group. So what happens if your group is non-abelian, and several people try to expand this Pontryagin duality to non-abelian groups, and Enoch and Schwartz, for instance, they did it with these Katz algebras, and they have some solution for this on a von Neumann algebraic language. But here also in this compact quantum group language, we can define a dual, and this is, so the sketching it is like this. So generalizing Pontryagin duality. So if we take a compact quantum group, and then we take the non-equivalent unitary representations, so we take these irreducible representations, and we take this algebra A0 as before. Then we let B0 be the space of all linear functions on A. For all linear functionals on A, given by X is mapped to H of AX for A in A0. Okay, so we take an element from A0, and then we apply the Haas state to A of X, to A times X, and this gives me a linear functional, and then B0 can always be written as a direct sum of matrix algebras, and we may find a co-multiplication on it. Which in fact does not map into algebra tensor algebra, but into the multiplier algebra. So some nasty detail at this point. So this is into the multiplier algebra, and by definition this is then a discrete quantum group, and it's the dual. So if we complete it, then it's the dual of the quantum group. Sorry. So it yields a discrete quantum group, which is, by definition, direct sum of such matrix algebras with a co-multiplication into the multiplier algebra. And this is the dual quantum group, and there is some statement like Pontryagin duality with these dual quantum groups. But again, so this is somehow a bit the survey part of the lecture. I just wanted to mention that this exists for those that are interested in taking direct sums of matrix algebras and having some quantum structure on it. Then you're in the business of discrete quantum groups, and there's some, and the theory is somehow dual to the theory we developed here before. Okay, so is there a reference? This again, Maas Vandale, section 8. And maybe let me end with the definition of this tensor product and the U bar. I'm sorry, maybe I should have put this a bit earlier, but I want to write it down at some point explicit. So if we have U and V, then the tensor product is given by this. This is again a representation, and the conjugate is given by this definition. And we have that if one is irreducible, then also U bar is irreducible. And if in addition it is unitary, then U bar is equivalent with a unitary representation. Okay, so these are some facts about the conjugate that we will need later. So next time I will do Tanaka-Krein, and Tanaka-Krein will inspire us to give a definition in terms of some combinatorics, namely these easy quantum groups. So next time I will define the easy quantum groups and give some overview what they are used, why they are useful, and what they are the main properties or the main, let's say, path people follow when they study it. And then on Friday we will classify them and give some examples. And next week then some applications. Okay, so that's it for today. Thank you.